talk about while we wait. So, how I wanted to start this off was just introducing the panelists, myself, to give you guys an idea of what we work on in our day jobs, and then I wanted to get into. There's a lot of these buzzwords that this panel is titled with. I'd like to define each one and ask the panelists questions about each one of these, right? So I want to do a deep dive on what cognitive architectures actually mean, and then I'll ask panelists questions about that stuff. Um, I wanted to understand how agents can use memory. How do you compress memory? How do you deal with kind of managing memory, and then also dealing with a limited context size for language models? I also wanted to see how we can talk about and understand planning and long horizon reasoning, right? So if you think about a difficult enough task, you can almost think of it as a language model executing consecutive steps, anywhere from 20 to 50 steps, depending on how uh, difficult the task is. I wanted to ask about how you can use agents to execute those steps. Um, and then I want to get more into multi-agent systems. So these are not just language models interacting and invoking other language models, but human in the loop systems as well. And so all of our panelists work at companies that are developing these cognitive architectures, these memory modules, these multi-agent interaction frameworks. So I wanted to touch on that. And then I want to get to the last point, which is how do we take the experiences that these multi-agent human in the loop systems that have had in the past? This could be customer interaction data, this could be logged interactions. How do you take that information and now make the system learn so that the thousandth time a system does something, it does it a lot better than the first time that it did it. And then I wanted to end off with future direction. So I've got a lot I wanted to ask a lot of questions and give people a lot of kind of a deep dive into the topic at hand. Um, and so hopefully we get through it all, but uh, let's see if we can. Is the panel ready? Hey, Lorenz, how are you doing?
I'm good. How are you doing? Happy Monday, by the way.
Yes.
Should I kick it off? Like do intros
All
or
right. Awesome. I'm not sure.
Yeah, Zain, we
Oh,
can
okay.
go ahead and get started. Right. So
I'm seeing
let's go.
everybody.
Yeah,
Okay,
yeah.
okay.
So,
Yeah, sorry.
yeah.
I had to scroll to see everybody was present. Okay,
Yes.
cool. So I'd like to start off with introductions. So I'll introduce myself and then I'll throw it over to the panel to give an overview of what you're working on, your company as well. So my name is Zain Hasan. I'm a staff engineer at Together AI. Together AI is AI native cloud. It's powering a lot of the training and inference workloads that a lot of leading Gen AI companies are working on. And we do everything from providing compute to kernels to run these Gen AI models that you're hearing all about. So maybe I'll throw it off to Lorenz. You can go next.
thanks, Dan. Everyone, my name is Lorenz. I lead the open source team at Crew AI. And to those who don't know what Crew AI is, it's the leading multi-agent orchestration platform. So we pretty much kind of power and help companies like DocuSign to PwC to Royal Bank of Canada kind of one build, but also deploy and iterate and monitor their AI agents within these enterprise systems.
All right, awesome. Thank you, Lorenz. Next up, Kartik.
Thank you. Hey everyone, I'm Kartik. I am head of AI at Wand AI. So at Wand, we basically are building the agentic operating system for hybrid workforces. So there is a lot of overlap to things that Lorenz mentioned as well. You know, we're trying to basically build a cognitive architecture that allows both human workers as well as agentic workers to kind of work together, organize workflows, and then engage in automation, you know, ranging from kind of simple automation all the way to full automation of departments and companies and so forth. Before I came to Wand, my background is actually as a researcher, as a research scientist in planning and cognition. Back in the, so I like to say that, a decade or so ago, I was working on agents before agents were cool. At that time, agents were robots. They were actually physically embodied agents. But yeah, a lot of the work that I did both as a grad student and then during my time at IBM Research, it's coming back now. It's in vogue, and I'm hoping that we can talk about it at the panel. Things like planning, observability, replanning, memory, cognition, all of these things. So yeah, looking forward to it.
Awesome. Thank you so much, Kartik. And last but not least, Sarah.
Can you hear me okay? I'm not okay. I
Yeah,
think
I
this
can hear you
microphone's working.
fine.
Okay, cool. Hi everyone. My name's Sarah. I'm one of the co-founders and CTO of Letta, which is the platform for stateful agents. Letta basically came out of the MEMGPT project, which my co-founder and I, and also our lead research scientist, worked on during our PhDs at UC Berkeley. MEMGPT was kind of like the first example of a stateful agent that has like memory, can learn, a sense of identity. And so a lot of those ideas we built into Letta, which is essentially making it really easy to create these agentic services that are persisted, have memory, can be integrated into your applications. And today we work with companies like Built Rewards, Nokia, 11x to essentially help them build these agents that are able to learn.
Awesome. Thank you so much. So, during the introductions, there's a lot of concepts that were mentioned. So, I'd like to kind of define these concepts and then throw it over to the experts to answer questions about what's happening at the edge right now. I wanted to start off talking about cognitive architectures. And the way that I understand cognitive architectures, these are really the blueprints or the scaffolding within which all of these different modules sit, right? You have perception, IO, memory, the ability to reason and plan and make decisions, and then also to do tool calls and action things in the real world. So traditionally, a lot of cognitive architectures have been quite modular, where you could have a planning system that feeds into a decision-making system, and then you have memory that you're able to access. And more recently, we've been seeing kind of these all-powerful monolithic LLMs that do everything, right? They plan and then they do in context kind of management of what's been executed and what's not been executed. So I wanted to start off and just pose the question to the folks on the panel. How do you think today's language model-based agents do you think that they're modular architectures, or do they differ fundamentally from classical cognitive models that are more modular? So maybe we can go backwards. So maybe we can start off with Sarah.
Yeah, so I mean, I think there's kind of different ways that people like to think of LLMs. I personally kind of prefer like there's like the more like, oh, neuroscience, like cognitive architectures mentality, but then there's also kind of like the more like systems, like operating system mentality. And I think that abstraction is actually much easier to think about. Like because in the end, like an LLM is just a tokens in, tokens out. It's just like a string generation machine, right? And so all these things that we do, like tool calling, memory management, multi-agent systems, it's kind of like mapping down those systems into like this like LLM computer that's just generating tokens. So I think for me, I personally find it easier to think more so of the LLM as like a CPU, and essentially like the tokens that we're putting into it are kind of like a compiled program. And so I think, there's of course like different like agent architectures, different ways that you can structure things, manage the context. But I personally find that way of thinking of things a lot easier because I think it is more closely tied to the reality of what an LLM is, which is ultimately just, this token generation machine rather than something like a human brain.
Yeah. Yeah, and I know that Karpathy put out his Software 3.0 talk where he makes a similar analogy where
Mhm.
language models are really like a CPU or an operating system, and then you've got all of these different modules that you give them access to. Um, awesome. Karthik, how about your take?
Yeah, so I think I agree. I think a lot with what Sarah said. I think it's a great distinction between kind of more of the neuroscience. And I think now when we're coming into this modern paradigm, what we would often call neurosymbolic kind of architectures, right? Combining neural methods on the one hand and then putting them in a scaffolding of more symbolic methods versus kind of the more, operating system metaphor. But one thing I also want to talk about is a little bit of kind of a historical perspective, from the research or from the AI side of things, right? So cognitive architectures have been around pretty much for as long as AI as a field has been around, right? So people were working on cognitive architectures even in the 1960s and the 1970s. In fact, some of the earliest work in the whole field of AI as we know it was around these kind of well meshed out cognitive architectures that could actually run robots and actual real world systems and so on, right? What I see now, and I actually gave a talk about this last last week as well. What I see now is that a lot of the ideas from that time, whether they are in terms of communication between agents or they're in terms of the planning, the observing the world, replanning, all of that, a lot of those are coming back now as we start using LLMs for more and more complex tasks now, right? So essentially, I think what's happened is the engines, like the components in these architectures, have become more powerful, right? So we're replacing each of the individual components with specific models, right? So there are models that are good for long horizon planning, for example. There are models that are good for completion. There are models that are good for different things. So we have a powerful models now, but we still need a little bit of that determinism, because I think one of the big problems that people have had, obviously, with LLM based systems is that the consistency is just not there when you try to go from POCs to actual production level things, right? So one of the encouraging things, and for me this is encouraging because it shows that we're actually building on history and on the experience and errors of other people decades before us, is that people have been building these bringing in these ideas into various things, whether it is a crew AI or an autogen or an AG2, or whether it's a protocol like an A2A, MCP, whatever, right? A lot of these ideas from the past are actually now making themselves felt again. And I think this is somewhat the right way, because to me, at least, this is a very personal view. I might change this, if there are further advances. But to me, it seems like where we should be putting our effort into is not building larger and larger LLMs that can be more and more general and generic, right? But rather smaller, more specialized components or units, right? And then those units are embedded into these more symbolic structures in some sense, because ultimately that gives you more of a level of control and more customizability and more consistency, which is what businesses are looking for at the end of the day, right? Because like this big gap between the research and the POCs, and then kind of business applications on the other end, which is where all the money is basically this notion of can you break it down into individual components? Can you do credit blame assignment? If something goes wrong, can you tell me which component actually messed that up, right? And can you effectively gate the propagation of errors, right? So I think cognitive architectures have a very important role to play in that, and I think there's a lot that we can learn from the past as we try to kind of reinvent the wheel in some sense, right? So that's kind of my take on that.
Yeah. Awesome. I wanted to pull on one of the threads that you mentioned there, but I want to give Lorenz a go at the question, and then we can go into the next question after that.
Sweet. Yeah, pretty much agreed with Kartik and Sarah here. Like the LM being the core of our operating system as a developer tool slash framework kind of provider, right? And giving that perspective, think of like these architectural components that we have, the cognitive architecture as components that we have. So we have our LM that has now access to memory. Before it didn't. Maybe now, if you're using a framework like Crew, like Letta, for example, you have these modules that you could easily plug in and play. For example, if you want memory equals, just do memory equals true for Crew AI. For reasoning, reasoning equals true. So these are like components that you could add on to your agents. You could add any tool that you want, right? You could observe and monitor that. And these are like kind of like special abilities that your LM kind of has out of the box. There are some reasoning models to Kartik's point, like as these models get better and better, some of these abstractions or components kind of are now built in within like the inference models, right? But if you were to put it from like a perspective of, you might want specialized LMs for specific types of use cases, right? Maybe you don't need a reasoning model, but you need memory. So these are kind of like the things frameworks give you out of the box. They're kind of battle tested. They're used by, you know, enterprise companies, but at the same time, it's giving you the right tools that you would need to make that decision for. So if you have a particular use case that you have in mind, you may not need like the biggest of models, right? Maybe a 8 bill parameter model with memory and the right tools, maybe even fine tune for particular use cases are kind of enough. But to answer your question, yeah, I think they're from a perspective of components. Think of it like having a toolkit, right? You have an LM that's kind of in the center of all of that, and you can bring and pick and choose what tools you want to include, whether that be a framework or a singular agent that you're making yourself, or an LLM call.
Awesome. Thank you so much. So what I wanted to do for maybe the next half an hour is essentially pick each one of these tools that all of you have mentioned, and get your understanding of them, and ask questions that the community is kind of grappling with. So the first one, and this is the one that I'm most interested in, is memory. So Lorenz, you just mentioned that you've now given these language models access to memory. They without connection to an external database, or a classical, like a vector database or a classical database, or even in context memory. Really, the only memory they have is what they've kind of distilled from their pre-training and post-training, right? So I wanted to start off and kind of pose the question of, how do you think of memory, and what are the different types of memory that you can give to these agents?
Yeah. So within Crew, we have kind of like the same similarities of like the SOAR kind of cognitive architecture when it comes to like memory systems, right? We have episodic memory, which is kind of like long-term memory where you can self-learn and evaluate over time. We have semantic memory, kind of like knowledge sources that you could plug and play. And then we have procedural memory, which is kind of like the rules that you have. For procedural, we have something called entity memory, kind of like remembers certain things and attributes, kind of like your writing style to who's important in this particular company. We focus our memory a lot when it comes to orchestrating multiple tasks together. So instead of like just remembering a birthday, for example, it's remembering how are you passing in tool inputs for a particular like task. We have long-term memory that does a self-evaluation after every task gets executed. And that self-evaluation has a suggestion on how it can improve and like a score. It uses LM as a judge to calculate all of these things, but that's kind of like how we see a crew of agents kind of self-improving over time. And if you were to picture what a crew is, it's multiple agents, right? It's not just one agent. Each agent has its own knowledge store and memory store and states, if you're using like a flow, for example. But together, it's kind of like, how do we orchestrate a automation use case versus like a chatbot use case? So think of an example being like, let's do lead enrichment. We're pulling data from HubSpot. We're trying to enrich this user using maybe something from online. We're trying to find their LinkedIn. So the tools that come into that, the memories that we generate, like entities, like who's important for this type of company when it comes to like a lead enrichment, what company do they work in, right? These get stored as memories for future iteration, future executions. So from that perspective, our memory is kind of like coupled towards automation and agentic like pipelines, you can say, versus like, oh, when was my birthday, right? So I think this is kind of like the road we're taking when it comes to like memory systems, more so than anything else.
Awesome. I'd like to go to Sarah next, and I'd like to kind of augment the question a little bit as well. I'd like for you to talk about the kind of the multi-tier memory system that Letta has, but then maybe also touch on practically how those multi-tiered different memories are implemented. So a lot of the community is kind of grappling with all sorts of different databases, classical databases, embedding approaches. So how does Letta deal with this?
Yeah, so I think this actually just comes back to, once again, the fact that like LLMs are just text in, text out machines, right? And so the way that we think of memory is there's, or I think the way most people think of memory now is there's kind of like two tiers. There's the memory in terms of like the state or what information's in the context window, and then there's also external information. So stuff that's outside of the context window, but it's somehow accessible to the LLM, whether it's through like tool calling, having like another agent retrieve things. And I think like this external form of memory is like what most people think of as memory. Like whenever you have like plug in memory, it's almost always just like some RAG-based thing. So, if I add like a memory MCP server or something, that's all that's essentially doing is just like fetching some records that I have in some external storage, bringing them back into the context window. And so now the LLM is like aware of that. But I think memory, it is actually like a lot more than that. Because I think like our DevRel actually had like a pretty good way to put this, which is that, memory, essentially explaining that like memory is not just a matter of like doing RAG or doing recall. And I think the example he gave was like, recall is remembering that you hit me. Memory is hating you because you hit me. A bit of a violent example. But I think that does really get to the crux of it, because I think with these RAG-based systems where you're just retrieving potentially relevant records into the context, like, maybe the last user message, doing some embedding similarity or some like graph search over like some external system and bringing that back into context, all that really gives you is recall. So if you want to have more of like an agent having an ability to learn or to like adapt its persona, you need to have something that's more like system prompt learning. So essentially rewriting the actual like context of the agent over time. And the way that we did that in MemGPT, I think MemGPT was kind of like the first example of this. There was just like a human section and a persona section inside of the context window, and the agent had the ability to edit those portions of its context window. And in Letta, we've kind of generalized it more to have something called memory blocks. So essentially the context window is broken up into multiple kind of allocated sections of memory or context. And the agent is able to essentially like rewrite like, maybe the human section or the organizational section or the general purpose or like tools used section. And so through this, the agent is essentially like continuously like rewriting the system prompt. And that's kind of what allows it to actually kind of change its own instructions in a way that I think is much closer to learning than these more like RAG-based approaches. And we also had some recent work called like sleep time compute, where we actually offloaded a lot of this learning onto a different agent. So now in Letta, like you can actually choose a new agent architecture where it's not just a single agent that's modifying its memory, managing its memory, doing retrieval. It's actually one agent that's just talking to you as kind of general purpose. And then it has another agent that's essentially working in the background to do memory management operations. So that other sleep time agent is getting all the conversational history, all the events that are happening. And its sole purpose is to just rewrite context to make sure that the primary agent is, as adaptive as possible, learning as much as possible. And that's really only possible because of the way that we architected Letta. So everything in Letta is essentially persisted in the database, including these context blocks. So you can do really cool things like allowing different agents to share context blocks. So that's kind of like shared context, where if either agent modifies it, it's propagated to all the agents that are, attached to it. So you could theoretically have like, synced organizational memory, stuff like that. And the blocks are also standalone. So you can always like kind of query a block that's about a specific topic. We have a really cool example agent called like Void. That's like an agent on Blue Sky. And Void is kind of interesting because it's swapping out its context blocks continually. So it always has like 10 context blocks about different users. And depending on which set of users it's talking to, it actually like swaps out which set of context blocks it has. So that's kind of like another layer, I guess, where like you're doing retrieval on like the pieces of context themselves and then also rewriting those. So yeah, there's like a lot of different crazy things you can do, but I think ultimately it does just come down to like, what is stuff that's stored in context that's being rewritten either by the agent itself or something else, and then also what is like your external store. And I actually think like the details of a lot of these things like don't really matter. It's just in terms of like the in context memory, it's basically just like replacing the text that you have, right? And I think for external stores, like, there's a lot of things that people do like graphs or like, just embedding search. You can actually even just use like grep and files. We did like an experiment with that recently and it worked surprisingly well. But yeah, I think that kind of just depends like more on your application and the details of what you want to store. But it's like not actually as impactful as you might think as compared to like system prompt rewriting.
Awesome. Karthik, I'd like to pose the same question to you, but touching on some of what Sarah mentioned around thinking of memory as system prompt rewriting. One of the very practical problems that that developers and the community has is running into context length issues. So if memory really is kind of making sure that the system prompt is fresh, all of the information that you put into the language model that you condition its generation on is fresh. how do you deal with kind of compressing those memories, having to compress those memories when you run into context length issues? State-of-the-art models are about 200,000 for a lot of these models, Gemini about a million, 2 million. So maybe how can we deal with that?
Yeah, no, I think that's a great question. In fact, I think that's a question of very, huge practical importance because, like you said, developers who are making things right now, they're working mostly with those things, right? So the way I think of this is, so there's a phrase that's been thrown around a lot in the last 1 or 2 months. I'm sure all of you here on this call have heard it, context engineering, right? Which is basically this notion of you have context, you have context windows, right? But now what you need to do is you need to kind of impose some sort of structure and some sort of hierarchy and some sort of engineering basically on top of that context itself. And obviously then that problem comes up because you have models whose context windows are being exceeded by what we want to give those models. And also remember that even if a model advertises itself as a, I don't know, 125k or 200k or 1 million context window model, it's not necessary that it's going to actually process all of the 1 million tokens that you're putting into that context, right? This is a very well studied and well known effect in language models at this point, right? Like the whole notion of they models tend to focus more on the beginning and the end of the context, and there's this whole needle in a haystack problem in the middle of it, right? It's like the thin non-existent middle. So the way that I like to think about it, and I actually want to go back, I actually really liked the aphorism that Sarah used about recall versus memory, right? That the difference between remembering that something is bad for you versus hating it because it was bad for you. And I actually want to extend it out one further step, right? So there's recall, there's memory, but then there's also this notion of knowledge and wisdom, right? So the idea there is that if something has happened a bunch of times over and over and over again, right, then it actually is knowledge that you can encode and write down, right, so that it actually becomes something that you can use for future computation and for creating things in the future and so on. And the reason I talk about this is because, again, I think a lot of this panel for me, I'm going to be the guy who keeps saying, but remember this stuff that was done in the past, right? Which I think there is a lesson there for all of us who are building and developing, right? Um, One of the very powerful tools in AI, over the last 20 years, but of course the work has been going on for many decades, is this whole notion of knowledge graphs, right? So the idea there is that, you can basically extract from the context that is there, and you can start making these structural representations of knowledge itself, right? So a knowledge graph at its simplest is basically a graph, nodes and edges, and then the nodes are basically concepts or entities and the edges are relationships between them, right? But one of the things I think that could be really powerful is the distillation of the knowledge of the world, right, into these structured graph representations. And that's one step, representing that knowledge. The other step is teaching our LLMs how to actually use, access and use the knowledge that is there in these graphical structures. For that, you need obviously a bunch of different tools, and you need a bunch of different models to be trained to access that. And the reason I think that that's so important, right, is the world's knowledge can be many different things depending on your application, right? It can be knowledge about your particular company. It can be knowledge about a particular use case. It can be knowledge about a particular country's, sovereign, I don't know, wealth things, for example, right? So these are very customizable things. And if you think about it, this is the way that we as humans tend to interact with stored knowledge and stored context, right? This is the way that let me say older AI agents, pre-LLM AI agents, this is how they used to access that as well, right? And so for me, this is very much tied into this concept of memory, because knowledge is nothing but memory that has been aged like fine wine, right? If you think about it, knowledge, whether it is knowledge that we have or knowledge that's been passed on through previous generations or through teaching and so on, is basically just memory and context that has been, stacked up layer after layer after layer until you know that, okay, this is just received wisdom. I can just, kind of depend on it and so on. Of course, there are other problems on the other side of it. There are biases that get built in and all of that, right? But ideally, what we want our agentic systems to be heading towards is the ability to both represent memory, right, in that way, and also use that memory in that way. And I think one of the places that we can turn to, just like we've had all these advances, incredible advances in the last 1 or 2 years, including all of us here, we've been working on some of these. We've had advances on cognitive architectures, on kind of interoperable platforms and tools and things like that. I think what's coming next is also advances in how to represent context, how to represent knowledge, memory, all of these things, right? And how to actually have models that can learn how to use these, right? These don't need to be huge models, right? You don't need to have multi-billion parameter models, because remember, if you're able to externalize the knowledge and teach the model how to actually retrieve the information that it needs, right? You no longer need to store all of that information inside of the model during pre-training. And I think that really will help with scale up. It'll also help with, I think, interpretability, right? Because once the knowledge is stored outside, it automatically becomes a lot more interpretable than knowledge that is inside a model during pre-training and so forth, right? So I think that's my kind of maybe slightly tangential take on memory, which is that we need to focus more on systematizing it into knowledge in some sense.
Awesome. So this actually gives me multiple ways that I can go forward now. So right now I might want I want to skip the next two things that I wanted to talk about and get into actually the learning aspect that you all talked about. So how I want to take the conversation is going from memory, and then seeing how can agents, how can these language models that are token in, token out, how can they learn from iterative previous memories, previous experiences? I'd like to touch on that. How do you, is it a matter of kind of reinforcement learning, fine tuning, or is it a matter of context engineering and retrieving the appropriate context for the task is at hand? And so this time, maybe we can do kind of a round on this, and then we can get into the other tools. So, Lorenz, maybe you can start us off.
Yeah, I'm gonna touch on two things that we currently do, and then kind of like the future of how I potentially see this from the perspective of how we do it at Crew. So we have two ways for kind of like self-improving, right? One is through reinforcement learning with human feedback, and again, kind of like just painting a picture of how that works in Crew is like for every task that gets executed, it will pause and it will give you a suggestion, like a field where you can give a suggestion on how it can improve over time. And you, as a person or as someone who's administrating this agent workflow, you have the ability to type, like, hey, maybe use these types of websites when you're scraping the web. These are the types of entities I want enriched when it comes to like a lead, for example, that I'm trying to search for, right? So after every task, usually in a crew, there's like 2 to 3 tasks per crew that we have. These get stored into memory for future iterations to load. It's a little bit on like the simpler end, super practical. We just re-inject that into the prompts later on as like memories of how it can improve. There's like a suggestions on kind of like the prompt on the prompt layer that we inject for future iterations using that retrieved memory store. When you use memory equals true within Crew, so this is the second piece, long-term memory, after every task, it automatically scores itself. It gives a suggested score of like how it did based off a task output. So when you define a task in Crew, you have something called description and an expected output. Expected output is kind of like your criteria of success, right? So this is something we require by default when you're defining an agent task. And what we do is using LM as a judge, we take a score based off like the task outputs itself against that expected output. And we store that into long-term memory. And again, kind of like the same cycle as reinforcement learning with human feedback, kind of like the same concepts of this task evaluator gets stored into memory. So kind of like think of a way of how it can improve itself. That's kind of like the prompt and score that we give it. The future of how we can take this to Kartik's point is like this concept of context engineering. Can you, as an engineer, can you, from a using a framework perspective, right, have the toolkit to define how this kind of context is used, stored, and retrieved, right? So bringing all these together, you have reinforcement learning with human feedback, kind of ties into long-term memory for like a agentic self-improvement over time. And then for the future, for like developers, not the future, but for engineers who want to have more control over this context, this is something where context engineering comes into play.
Awesome. Sorry, I'd like to get your take on this, but then I'd also modify the question a little bit, which is, um, how do these language models, how do you think they can learn from past experiences? But then also, how do you allow users or developers to inject hard constraints? So let's say you want to alter the behavior of the language model. How can they learn from kind of human imposed constraints or business imposed constraints as well?
Yeah, so I mean, I think with Letta, like the primary mechanism for learning is essentially like, what we were talking about before, which is rewriting the memory blocks, which eventually go into the system prompt. And yeah, I mean, if you just try Letta today, if you like, tell it like, oh, like start using emojis in your responses, or like, don't do this, like you'll see that it'll often actually update its memory blocks or its memory in context memory to, basically like write its own prompt to give itself instructions to do that in the future. So I think that's kind of like the most like basic form of learning that we support. In terms of kind of, more like reinforcement learning based things, I think this is like a tough problem. Like my co-founder Charles, his PhD was actually in RL, and he actually I think is like a big believer in more just like using kind of like using that for as like another form of like system prompt learning, or like potentially like using the feedback that you get from the agents. So like in Letta we do have like a thumbs up thumbs down that you can put for different responses. So eventually that could be used as essentially like a mechanism of feedback to potentially do like automated like prompt tuning, maybe similar to something like DSPy, to essentially encourage those agents in the long run to kind of like rewrite their prompts, or like to automatically rewrite the prompts to potentially like, do better in whatever the task is. Another kind of related topic is also like sleep time compute, which I mentioned before, which is essentially having, these agents which are offline. And so these agents, because they're not like part of the conversational agent, they can go back through previous histories. They can maybe revise feedback to essentially like process information and then generate like a better prompt, or like better like in context memory blocks from that. So I think these are like all things that you can do. But yeah, it's definitely hard to get right.
Yeah, for sure. And Karthik, I know that Juan's put out work on this as well, where you've talked about language models benchmarking performance, current state of the language model, retraining and replacing to improve performance across those benchmarks. Can you maybe talk a little bit about how these systems learn from experience and human input as well?
Yeah, actually, that's great. I actually wanted to pick up also on the part that Sarah was talking about with respect to reinforcement learning, right? So we've been doing a lot of work also at WAND that is very related to that area, right? So what happens is we get a lot of information that comes in from, let's say, our customers, right? Both in terms of information that they have prior to actually starting to use the system, right? So these are usually in the form of documents and process knowledge and so on, right? And then there's also usage information as they start using the system, as they start chatting with it, as they start giving it goals, they start giving it also feedback in terms of how it's doing and so on. And so the big, the billion or $1 trillion question is, how do you actually use all of this knowledge to improve the performance of the system? I agree that I think there is a lot of potential in various reinforcement learning methods, right? But one thing I'd like to talk about is there is also a drawback to a lot of this, right? Apart from the obvious drawbacks of like scale and time and compute and all of that stuff, right? One of the fundamental issues with reinforcement learning, right, is it can tend to kind of over optimize. It can tend to go into a bit of a hole, right? And so nowhere is this more evident than when you're trying to use reinforcement learning in order to train models to do better on challenging domains. So we wrote a paper back in, I think, March or April. It's currently under review at the NeurIPS conference. We're hoping for the best. But basically, that paper, which was about concise reasoning, was talking about this effect where as the length of the output generated by the model gets longer and longer, right? The accuracy of your model overall actually starts dropping, right? And the problem here is essentially that in some sense, and I'm greatly oversimplifying here, I'll drop a link to the paper and the work for people who want to read it in more detail. But the fundamental concept here is that the model is basically learning to overfit on specific instances, right? And so it's kind of losing a lot of its predictive power in some sense. So the fundamental idea behind the paper that we wrote was, if you can somehow restrict these models to shorter outputs or smaller outputs, right, you can actually greatly improve the accuracy of those models. And the way that we tested it is we took a bunch of these smaller models, like a 1.5 billion parameter model and a 3 billion parameter model, a 7 billion parameter model. And we said, if we were to impose this artificial constraint of now outputting much shorter responses, right, can we actually increase the accuracy of the model. So you actually get two wins, right? You get one win in terms of the accuracy improves, and your second win is that you're greatly reducing the number of output tokens, which is ultimately the biggest cost when you're calling these models, right? And so the TLDR of the work, and again, like I said, I'll put a link to the paper right after I finish speaking here, was that we can reduce the number of output tokens to almost 1/3 of what it was previously, while preserving or in some cases even improving the accuracy on challenging domains and challenging problems, right? So I think there are algorithmic advances that we can make. In this case, we're talking about, RL, we're talking about reinforcement learning, but there are a lot of algorithmic advances that we can make in order to make these models more accurate, but also less expensive in some sense, right? And then one last thing I'll also say, which is slightly different, is in terms of personalization of these models. We've also been doing a lot of work at Wand, since basically the beginning of this year, where sometimes because you have a lot of usage data, instead of just taking kind of the +1, -1, just the thumbs up, thumbs down, you can also take that usage data and you can train adapters, right? So you can train like a last layer on a smaller model, right? Which can be used as an adapter for a particular company or for a particular use case, right? So these are kind of use and throw. And in fact, we even got it down to the level where we could train adapters for specific users, right? So Zen, for example, if you're using, let's say, our product, right, and then you have a set of interactions with it, we can actually customize the performance and the behavior of the model to take into account everything that you have talked to it about. Now, obviously, there are a lot of different problems that need to be solved in that space, but these are two different things. Like the RL approach, I think, is a much more general, heavy-handed approach in some sense, versus the adapter approach, I think, is much more niche and narrow and like targeted towards a specific use case or a specific person, a specific company, and so on. So yeah, I think that's kind of my view on that. That I think RL is very powerful, but we also need to be a little careful about how much we end up optimizing with reinforcement learning techniques.
Yeah, and I wanted to pull on one thread. If you can optimize the number of output tokens, I think the third benefit of that is also it's easier to manage the context, because if you think of a language model or an agent task to successfully complete a difficult task at hand, it can take anywhere from 20 to 50 to 100 consecutive executions. These could be tool calls, feeding the input back in, reasoning over that. And so if you're more efficiently managing that context, then you're less likely to run into those long context issues that we talked about. But this is a good segue into the last topic that I want to talk about, which is this long horizon reasoning and planning. Um, Difficult tasks require multiple successful language model calls. So maybe I wanted to pose this question to everybody, which is how do your systems handle these long horizon task completions and reasoning? And specifically, the interesting thing that developers are having to deal with is what happens if the system or the model makes an error on the 10th step? How does it execute on the 11th step, and how does it go forward? So maybe you guys can talk about how you're dealing with that issue, and maybe what are some of the future research directions to help deal with planning and long horizon reasoning. So I'll throw it over to Sarah, and then we can go from there.
Yeah, so we actually had a like some recent like research work that's currently going into a paper called like Recovery Bench on this topic. It was essentially doing like a comparison on terminal, I think yeah, Terminal Bench, which is like this terminal use benchmark. It's like a pretty good benchmark for like these like long horizon complex tasks in the terminal. And there was this kind of interesting result where depending on which model you're using, the ability of the LLM or agent to recover actually differs quite a bit. So I think Claude Sonnet is incredibly good at coding, so it's obviously number one for like doing the task in a fresh state. But in terms of like the recovery state, so like once you kind of pre-fill the agent with a failed trajectory, we actually found that GPT-5 and I think Gemini also like bumped up in the ranking. So GPT-5 was like the best performing model. And then yeah, I think there's also been work from like SweBench kind of showing that like if you randomly alternate between like GPT-5 or like different models, like you get like better results than just using a single model. So yeah, I do think one interesting aspect is like, maybe throughout the agent's lifetime, you should be changing what model you're actually using. So maybe if there's a failure, you should like switch to like a more like an LLM that's better at recovery. So I think like that's maybe one really interesting angle. And then yeah, I think in terms of long horizon tasks more generally, one thing that we've actually found is that memory plays like a surprisingly important role here, because going back to this idea of, rewriting the system prompt, rewriting the context blocks, that's essentially like a way for the agent to be organized about what it's doing at the moment. If you've ever used Claude Code, you might have seen like, it's always making these like to-do lists and then checking off the to-do lists. So I think having something like that happening inside of the agent's memory is actually incredibly important for the agent to understand what it's doing, to not get derailed, which is ultimately like the biggest risk. The agent like blows up its context, forgets what it's doing, and like fails a task, on iteration number 10. So yeah, I think like memory rewriting, making sure that you're consolidating the context window, avoiding derailment. These are all like things that are like really, really important and something that we focused a lot on Letta. And so I think a lot of these tasks, like if you actually do that context management right, you can get really, really far. So with Letta, we actually, I think like a couple weeks ago, made like an example, just like terminal use agent. And like terminal use is like not like our main thing, obviously. But despite that, like it was actually like the #1 like open source implementation at the time for Terminal Bench, just because like a lot of the built-in features of Letta for being able to write to context, being able to modify context over time, and then giving the agent the tools to do that, that actually turned out to be extremely useful for creating an agent that can do really long horizon tasks, like the ones in Terminal Bench.
Awesome. Thank you. So we're almost at time here. I've been given 6 more minutes to take some audience questions. So I'm just let me look through to see if there's some good questions. There's a lot of questions. So let's see. Uh, Yeah, so this is a topic that I wanted to talk about, and I'll use this question to talk about that. But I wanted to pose this question about single language model powered agent systems versus multi-language model powered agent systems. And there's a lot of debate in the community around when is the added complexity of multi-agent systems worth it versus when should I just stick with the most powerful model that I can find. And Sarah, you mentioned about how it might be worth swapping out that most powerful model to recover. But how do you guys think about going with multi-agent systems versus just using the most powerful model and letting it fix the trajectory to these long horizon tasks and task completion? So I'll throw it over to Lorenz for this one, maybe.
Yeah. So again, it always depends on your usage, and that's kind of what we tell customers and our users, right? There's two orchestration types that we have at Crew. One is a Crew, which think of it like a Waymo. You have a bunch of agents working together, and it's autonomously getting to its end destination. Then you have something called flows, which is more deterministic. You have it's an event-based orchestrator, so you have a start method, you have routers, and in between are like each node can have regular Python code to single shot LM calls, singular agents, or inside that could be a crew. So how we've distributed like a 2x2 is like depending on your use case, if it's high complexity, high precision use cases, you might want the best models that you can get, right? For lower complexity, lower precision use case, think of like a lead enrichment. It's not as complex. You don't need the best of models. You might need tools to get you there. But for example, when it comes to high complexity, high precision use cases, for example, we had a customer that's filling out IRS tax form data. You can't make a mistake for those, right? So maybe using the latest and best models for something that could do OCR really well, or something that can do image processing really well, or image understanding really well, or even writing into like tool calls specifically to writing into those forms. It just depends on your use case. So like, again, if you were to have a framework or framing for this, if it's a high complexity, high precision use case, potentially use the best models you can get. If it's a lower complexity, lower precision use case, you might get away with smaller models as well.
Awesome. Kartik, I'd like to hear your take on this because you've mentioned the use of small, very small, fine-tuned models that are specialized, and that tells me that you lean more towards the multi-agent system. So I'd love to hear your
Yeah,
take on that.
yes. I think I will keep it brief. I actually think that this is going to be an emerging field in the next 6 months. So to everyone here at the conference as well, and I intend to also follow my own advice in some sense. So remember how RAG, I think maybe 2 years back or a little bit more, right? RAG became this whole thing where there were so many different options. You can choose a different vector DB. You can choose your, the model that you want in order to vectorize the data, and a lot of other different things. I think this question of, a single agent versus multi-agent, or single model versus multiple models, is also going to get there, right? And so in some sense, there is no good answer. There is no correct answer, right? I think it's going to be very use case dependent. It's going to be very application dependent, right? Obviously, you get a lot of immediate trade-offs if you go with like a large model, let's say, versus a bunch of smaller models. There's communication overhead, and there's all kinds of other overheads when you're trying to manage the output from a bunch of different models. But it might net end up being cheaper for you, right? Versus using a much larger model may not always work, both from a cost perspective, but also your larger model may not be trained on specific data that you want it to be able to use or access and so forth, right? So I think this whole notion of architecture engineering, for lack of a better phrase or like better term, I think is going to be very important in the next 6 months to 1 year, right? And if you are someone from a hands-on perspective, if you're someone who can actually build, both with a single model, but also with multiple models, and you can actually give stakeholders that choice, right? You can tell them, you can go this way or you can go this other way, and let me advise you on what will work better and what will work worse when you do this. I think you stand to make a lot of progress, make a lot of money, whatever your metric is, right? So I think that's kind of what I'll say about it. I don't think there is one correct answer, but I do think people should be focusing on how to actually turn this into an engineering field, not a science field, right? How do you turn this actually into something that can be engineered? So yeah.
Awesome. Thank you. And we've just got 1 minute left. So Sarah, I'd like to throw the same question over to you, and then we'll go over to a break.
Yeah, I mean, I think I maybe disagree a little bit in that I think you'll often get the best performance from having like one really good agent like running on like a really good model. And I think part of the reason for this is because ultimately that's how a lot of these models are trained, right? Like in general, you want to design your systems around the way that you are kind of guessing that OpenAI and Anthropic and these other providers are training these models. And I think there's also been like recent blog posts from like Cognition and I think like Open Devin or Open Hands that was kind of talking about how like in these really frontier use cases like coding where you're really pushing the limits of what can agents do, they've actually found that like single agent systems are much easier to actually work with and engineer, or like just have better performance than multi-agent systems. I do of course think that there's cases where you want multi-agent systems. Like I think Anthropic's research agent was multi-agent. It had like multiple sub-agents with like specialized context researching, exploring different things with like one main agent aggregator. But I think in general, like for our users, what we kind of recommend is like starting with a single agent. And then if there's like reasons to go multi-agent, like for example, like maybe there's just so much context that you can't fit it into a single agent, then breaking it up into multi-agents. And then I think we also kind of suggest like, start with the best model and just a single agent. And then if you need to reduce your costs, if you need to kind of like, reduce the amount of context per LLM call, or like maybe use cheaper models, then break it down. But I do think it's really important to, because in most cases you will be getting the best performance from one really good model, to kind of start from that.
Yeah, awesome. Yeah, I wanted to end off with that because that's kind of a high-level decision that a lot of developers are having to make as soon as they start off on a problem. Do they want to go with a bunch of models or just go the easy route and use the best models? So we're at time. I wanted to thank the panel, and just to give a quick summary, we touched on cognitive architectures. We talked about memory. We then looked at how you can use past experiences, past logs of previous memories to then learn for future execution. We talked about kind of long horizon reasoning, planning, and then thanks to the questioner, we also got the opportunity to talk about multi-agent versus single agent systems that the community is debating about. Like Sarah mentioned, Anthropic put out a blog post on multi-agent systems. Open Hands and Cognition put a blog on maybe you don't need the added complexity of multi-agent systems. So I hope this discussion was useful to all the developers out there and to everybody that's listening. And I wanted to thank the panel as well. Thank you so much for your time.
Yeah, thanks for having us.
Thanks so much, folks.
Thanks, everyone.
Thanks, everyone.
Thank you.
We are going to take an 8-minute break, and we'll come back from the break.